Okay, in the previous couple of lessons, I've sometimes made reference to vectors, and now we're going to discuss them in more detail. So that by the end of this lesson, you should be able to distinguish between vectors and scalars, explain how vectors can be represented using arrows, and add vectors in one dimension using arrows, as well as knowing that it can work in two dimensions too. So in physics, you're going to work with two kinds of quantities, or two kinds of things that can be measured: vectors and scalars. Now, a vector has both magnitude, that's another way of saying size, and direction. So for example, we talked about displacement being a vector, and you might have a displacement of 5 meters, that's the magnitude, and then right would be the direction. Whereas a scalar just has magnitude. It doesn't have a direction. So for example, speed we talked about is an example of a scalar. So 5 meters per second could be the speed you're traveling with. Now, if we said 5 meters per second right or 5 meters per second north, that would now be a velocity, and that would be a vector because we're adding a direction. So we've seen several examples of vectors already. We've seen position, and we gave position the symbol x, and we put the little arrow over top of it to indicate that it's a vector. We've also seen displacement. And displacement is just the change in position. So delta means change. Change in position is displacement. And now in the last lesson, we saw velocity. And velocity, v with the arrow over top of it, is the rate of change of position. Again, the arrow over each of those symbols is what's used to show that it's a vector. As you saw above, when we write directions, we often give them in square brackets, so something like north or left or something like that. Now, you also already know a lot of different scalars. For example, mass is a scalar. Something can have a mass of 3 kilograms. That doesn't have a direction. We said that speed was an example. Distance is an example. Volume is another example. None of these have direction, so they are all scalars. And we can represent vectors using arrows, where the length of the arrow is going to show us the size or the magnitude of the vector, and the direction the arrow is pointing is going to be the direction of the vector. For example, this could be a displacement of 2 meters to the right, like that, an arrow like that. Now, if that's 2 meters to the right, then something twice as long would be a displacement of 4 meters. So here's the displacement of 4 meters to the left. Just a thing to note about vectors is that they're not fixed in place, so I can move them around, and all of this is still a displacement of 2 meters to the right, and this is still a displacement of 4 meters to the left. We only care about the direction that it's pointing and the length of the arrow. To make things easier on ourselves, when the motion's only in one dimension, like along a line, we can make things easier by just picking a direction to be positive. Often we choose up or right or north or something like that, and then we just use positive and negative signs to keep track of the direction. For example, if I put the origin here, and this is 5 meters to the right, then this displacement here could be written as 5 meters right, but you'll sometimes also just see it written simply as plus 5 meters. Similarly, if this is 4 to the left, then starting here and going to that position might be written as 4 meters left, or you might just see it written as negative 4 meters. Okay, so that can simplify things a little bit. Now, what if you have two different vectors and you want to add them together? Well, you can do that just by joining them head to tail. Let me show you what I mean. Let's say you start from the origin and you go through a displacement of 4 meters to the right. So I'm going to write that as plus 4 meters. So that makes this the 4 meter mark. And then after that, you choose this as your new origin and you go through a second displacement. Oop, I forgot my arrow over top there. You go through a second displacement of 2 meters further right, bringing you to the 6 meter mark. So obviously the total displacement is, if we start from the 0 over here from the origin, is 6 meters. And that's just obtained by adding the two of these things together. So this total displacement, I'm going to write this as displacement subtotal is plus 6 meters. What I've done is I've just lined them up so that they are head to tail, and then I start from the start here, and I start from the back tail, and I go to the front of this arrow, and I add the two together. And that works if you're changing directions as well. So let's say I start from the 0 here, and I go rightwards to the 5 meter mark. So this first displacement is positive 5 meters, and then I go from there back to the negative 2 meter mark. So now this displacement is from 5 back to negative 2. That displacement is actually negative 7 meters, but the total displacement here, starting from where I started at the origin and going to where I ended up, is just negative 2 meters, or 2 meters left. Again, what I do is I have lined them all up head to tail. I start from the tail of the first vector, follow it through to where it connects to the tail of the next vector, then follow it back. And to add them up, I start from the start of the first, the tail of the first, and I draw a little vector to the head of the last one. So I'm going from the start of the whole process to the finish of the whole process. And this, which is the same as this, is my sum total vector, also called the resultant vector. So again, to add vectors, you just add them head to tail. Now, I've only shown you this so far in one dimension, but it also works in 2 dimensions. Let's say that's your first displacement and that's your second displacement. You walk this way, then you walk that way. Well, you could have just walked this shortcut along here, and so the red is the resultant of these 2 vectors. Again, we add them by joining them head to tail. Okay, so in summary, we've talked about vectors. Vectors have both magnitude or size and direction, and we gave some examples of those. By the way, that's my and sign. And they're contrasted with scalars. Scalars just have magnitude. They don't have a direction. We've seen that vectors can be represented by arrows, and that's why we draw the little arrow on top of the symbols, like X with a little arrow on top. And we've also seen that you can add vectors by joining them head to tail. Okay, so that's your introduction to vectors.